Let's use the formula for cross-sectional area and the mechanical energy balance equation to determine whether velocity and pressure change linearly or non-linearly with diameter in the Venturi meter. We'll start by determining the relationship between velocity and diameter. We can calculate the velocity of the fluid at a point in the Venturi meter using the volumetric flow rate. To convert volumetric flow rate to velocity, we simply need to divide by the cross-sectional area. The cross-sectional area of the Venturi meter at any point is the area of a circle with a diameter equal to the inside diameter of the pipe at that point. Plugging this formula into our equation for velocity, we see that velocity is dependent on the inverse square of diameter, which shows that velocity changes non-linearly with diameter. A simple graph of the fluid velocity in the first half of the Venturi meter also shows this non-linear trend. Next, let's determine how pressure relates to diameter. Let's consider the energy balance equation between the Venturi inlet and throat, simplifying the energy balance between these points by canceling the potential energy terms and neglecting head loss in this short converging section of the Venturi. We can see that the change in pressure from the inlet to the throat is related to the square of the velocity. If we substitute the definition of velocity in terms of volumetric flow rate and cross-sectional area into this equation, we find the change in pressure is related to the inverse of diameter to the fourth power. This means that pressure is also heavily non-linearly related to the changing diameter of the Venturi. In summary, both velocity and pressure vary non-linearly with diameter. Notice that pressure decreases more rapidly than the velocity increases because of the fourth-order relationship between pressure and diameter compared to the second-order relationship between velocity and diameter.